Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today we will start to discuss about the first order differential equations. Okay. There are some subchapter that we will discuss. The first one is solution curve without solution. So if we have a ordinary differential equation in first order, so we have to sometimes we have to make a solutions. We can try to use many options. Like the first one, we can use a curve. So, and then another, we can use a separable variable and linear equations, and also exact equations, and also we can use a solution by substitutions. And another technique that I will introduce to you is direct integration. So another is direct integrations. Okay, so we start with solution curve without a solution. So why this is solution curve without a solution? Because it's little bit hard to solve ordinary differential equation even in first order using a curve. Okay, so the first one, we can begin our study in the first order differential equation. We will use a curve or solution curve, or we use a qualitatively to make a solution of the differential equation. So it means that to solve a differential equation, we can use a qualitative solution and quantitative. And the rest of the solution that I mentioned before is like exact analysis, and also the direct integrations and substitution. It is just a quantitative solution. And here, the first, we will try to use a qualitative analysis. So there's first one. If we're looking for the ordinary differential equations, so it means that we can determine the slope. So the derivative or dy per dx of y is equal to y x. Now give a slope tangent lines at the point. So assume that dy per dx is a function of x comma y x. So the value of function of xy represent the slope of the line, or a line element is called a linear element. So this is the solution of the ODE. So if it's like if we have a slope function in 2.3, so x is 2 and y is 3 here, so we have a slope. The slope is 1.2. So 1.2 is the slope of linear element at 2.3. So the solution curve passing through 2.3 is solution curve. So we can draw a curve past the 2.3. So if we have a 2.3 here, the black line, so this is the one of the solution curve. Exactly, we have many options to solution curve. It's like this one, or maybe this one, or this one, or this one. So many solution curve here to linear element at 2.3. So it means that I mentioned before that a qualitative solution is how to solve the ordinary differential equation without a solution, because so many solution curve can be determined at the one of linear element, like this one 2.3. So we can draw many options of the solution curve. So how to determine the best or the right solution curve? We have to the first one, we have to determine the direction of the field. So if we evaluate the f over the rectangular grid of the point, so we draw a linear element at each point of xy of the grid with slope fx, y. Then the collection is called a direction field or slope fields of the following dE or dyx, um, similar to function of x, y. So this is once of the illustration for you is why the solution curve is little bit hard to solve the ordinary differential equations. So it means that solving the ordinary differential equations by using the qualitatively is like without a solution. So it's another in another example you can see that it's like this one. So the direction field of dy per dx is equal to 0.2 xy is shown in figure 2.2a. And for comparison with figure 2.2a, some representative graphic of this family are shown in figure 2.2b. So it's like this one. So this is the direction field of dy per dx is equal to 0.2 xy. We can see so some solution curve is like this one. We can yeah, this direction like this one, or in figure B we make a graphic like this one. So this is a many solution curve. So this is to solve the dy per dx is equal to 0.2 xy, or y is equal to ce 0.1 x quadrat. So this is the solution of these equations. Okay, so this is another example you can write by yourself. And today, this is just overview for you why the qualitative solution in ordinary differential equation is like without solution. And I will introduce you a technique to solve the ordinary differential equation in first order by using the direct integration. I didn't put the PPT file in this, so um, I will explain to you by using this whiteboard. Okay. So what is the direct equation? Direct integration. So this is the direct integrations. Okay, it's like if I write the quadrat y per dx quadrat is equal a plus, sorry, okay, I repeat by again, y quadrat per dx quadrat plus dy per dx equal to x, like this one. So this is the example of ordinary differential equations, and the degree is 1 because you can see the degree here. Okay, so this is the ordinary derivative and not a partial derivation, so we can use the direct integration to solve these equations. Okay, so this is the second order. Okay, this is the second order because this is a 2 here, so this is the second order ODE. And the first part is linear, so this is the linear because the degree is 1. Linear is because the degree is 1, but the term here, the the term here is not degree 1, right? So because this is not a degree 1, so not a degree 1, so this equation is not a linear, so we can conclude that this is a non-linear ODE. Okay. Okay, so this is the example of ordinary differential equation. So if I jump to, oh, okay, what is this? Okay, if we have this equation dy per dx is equal to, this is the function of the x, so we can solve this equation by integrating both sides respect to x. So we can solve by using integration. So y, this is actually, this is the y, right? So y is equal to integral of fx dx. Okay. Okay, so we make an integration here and also integration here. So because of this is the integration of dy is equal to integration of dx, integration of fx, just like this one. So this is integration of this one is become y, and integration of this one become this one. So we can get that y is equal to integral of fx dx. So this technique is called direct integration. So we call it direct integration. So this is the easy technique, easy method to solve the ordinary differential equations. Okay, so for example, we have it's like exercise 1, example. This is the example number 1. If show that so that y is 2e x is a particular solution of ODE the second order ODE of this one. Okay. Okay, so how to solve these equations? So from this solution, so y is equal to 2e 2x, like this one. So the dy per dx is equal to 2 multiplied by 2e 2x, right? So so we make a differential of this equation, so become these equations. So this is the equal to for e like this one. So the second derivative of this one is become 2 for a 2x, so it's equal to 8, so like this one. Okay, so these equations minus 2y is equal to 0. Sorry. So it's equal to, we put this one and this one in this equations. So the second derivative of y per dy per dx is equal to 8a2x minus this one. This part is 4i2x minus 2, and y is 2y, and the y is 2e2x, like this one. Yeah, so this is 8a2x minus, this is 8, so 4, so 8a2x, so it's equal to 0, so no solution. So this is the non solution for this exercise. So this is one technique to solve. So if we have the ordinary differential equation and we have particular solution here, so how to solve this equation? We can use this one. Okay. So in example number 2, okay, I clear the canvas. The example number 2, derive the, what is the general solution of dy per dx is equal to 2x plus 3. Okay. Okay. So this equation dy per dx is equal to function of the x fx. So we can solve this by direct integration. Okay, so we integrate both sides respect to x. So we make integration dy per dx equal to integral of 2x plus 3 dx. So respect to dx, so we can get this one, integral of dy per dx is equal to integral 2x plus 3 dx, right? So integration of integral dy is y, so it become 2.5 of x squared plus 3x plus c. So we can get that y is x squared plus 3x plus c. And where c is a constant, arbitrary constant. Arbitrary constant. So we can, if we have some point here in this equation or this exercise, so we can determine the c. But if we didn't have any or another information of the point of this equation of this line, so we just make a solution like this one. So the solution is this one. Okay, so this is the example of direct integration. So if you have problem in or ordinary differential equation, with so we can the first one, the easily one, we can use the direct integrations to solve this ODE, and sure that this is the first order ODE. So this is this one is the first order ODE. So this is the first order ODE. Okay, I think this is the explanation of the direct integrations. Good afternoon. Bye bye.